Imagine something so powerful, so dense, that nothing, not even light, can escape its grasp. We are talking about the black holes, the universe's ultimate cosmic vacuum cleaners. For decades, we have pictured these behemoths as, some sort of very powerful, unmoving anchors of the galaxies, slowly devouring anything, everything that dares to wander too close. But what if I told you that sometimes these colossal objects don't just sit there? What if in their very moment of birth they get a kick so violent, so incredibly powerful, that they are sent careening across the cosmos at speeds unimaginable? Today, we are diving into one of the most mind blowing discoveries in the modern astrophysics, the gravitational recoil of the newborn black hole. This isn't just a theoretical concept anymore. For the first time ever, scientists have directly measured the incredible kick imparted to a black hole after a violent merger. We are talking about a phenomenon capable of launching a black hole at a speed up to 5,000 kilometers per second. It's over a million, 11 million miles per hour. Fast enough to cross the continent of United States in less than half a second. Fast enough to escape the entire galaxy. Before we talk about the black holes getting a powerful kick, let's briefly revisit what these incredible objects are. At its core, a black hole is a region of space time where gravity is so strong that nothing, no particle, or even electromagnetic radiation such as light can escape from it. The theory of general relativity predicts that sufficiently compact mass can deform space time to form a black hole. There are generally three main types of black holes, and let's discuss them one by one. The stellar mass black holes. These are formed when the collapse of massive stars, typically 3 to 100 times the mass of our sun, collapses into a black hole. When a star much larger than our sun runs out of fuel, its core collapses under its own immense gravity, leading to a supernova explosion. What is left behind, it's the remnant, and it's massive enough, and that is called the black hole. Next is the supermassive black hole, also known as SMBH. These are the true giants, ranging from hundreds of thousands to billions of times the mass of our sun. Almost every large galaxy, including our own Milky Way, is believed to harbor a supermassive black hole at its center. Our own Sagittarius A star is about 4 million times the sun's mass. How these colossal objects form is still an active area of research, but they grow by accreting gas, dust, and even other black holes. Then the third category is the intermediate mass black hole. These are more elusive class, falling between stellar mass and supermassive, with masses from few hundred to several hundred thousand masses, solar masses. Their existence is still being confirmed, but they are thought to be crucial building block for supermassive black holes. The crucial boundary around the black hole is called the event horizon. This is the point of no return. Once something crosses the event horizon, it is trapped forever inside the black hole. All paths lead to the singularity, which is in the center of the black hole, which is also a point of infinite density where the laws of physics, as we know, all break down. Now imagine just one of these cosmic monster, but not just one, but two of them, two black holes spiraling closer and closer together, accelerating to incredible speeds, destined for a catastrophic collision and merger. This isn't just a theoretical, physicist thought experiment. It's a cosmic ballet that happens throughout the universe. And it's precisely these mergers that give rise to our main event, which is the black hole kick. To understand the black hole kick, we first need to grasp another groundbreaking concept, which is known as gravitational waves. So, in the year 1915, Albert Einstein published his theory of general relativity, which fundamentally changed our understanding of the gravity. So, instead of an invisible force pulling objects together, Einstein proposed that the gravity is the manifestation of the curvature of the spacetime, the four-dimensional fabric that makes up our universe. Massive objects like planets, stars, and black holes warp these fabrics around them, and what we perceive as a gravity is simply an object following the curves in that space-time. One of the outstanding predictions of the general relativity was that the violent cosmic event, like the collision of black holes or neutron stars, would create ripples in the space-time that propagate outward at the speed of light. These ripples are what we call gravitational waves. Think of dropping of a heavy bowling ball into stretched rubber sheet. The ripples that spread across the sheet are analogous to the gravitational waves. For centuries, these waves remained a theoretical prediction. Frustratingly difficult to detect due to their incredibly tiny amplitude. They stretch and squeeze space by an unbelievably small amount, a change smaller than the width of the human hair across the distance of the nearest star. That all changed on September 14th, 2015, as on that historic day, the LIGO Laser Interferometer Gravitational Wave Observatory, that is an experiment that made the first detected gravitational waves on that particular day. What they observed was the faint but unmistakably chirp of two stellar mass black holes, about 29 and 36 times the mass of our Sun, spiraling into each other and merging roughly 1.3 billion light years away from us. This wasn't just a confirmation of the Einstein genius, it opened up an entirely new window to the universe. For the first time, we could hear the cosmos listening to the most extreme events that are otherwise invisible to the traditional telescopes that rely on light. Since then, LIGO, along with its European counterpart Virgo, has detected dozens of gravitational wave events, mostly from merging black holes and neutron stars. Each detection tells us a new story about the violent, dynamic universe. And it is this ability to precisely measure these ripples that now allow us to observe something even more incredible, and that is the gravitational kick. So how do the gravitational wave kick a black hole? The key lies in the word of asymmetric. Imagine two black holes locked in a deadly cosmic dance, spiraling ever closer. As they orbit each other at increasing speed, they are not just emitting gravitational waves, they are emitting them in specific pattern. Think of it like spinning on a sprinkler, spinning of a sprinkler. As it spins, water is, emitted in swirling pattern. Now, if there are two black holes were perfectly identical in mass and their spins were perfectly aligned and symmetric, then the gravitational waves they emit are as they merge would also be perfectly symmetrical. In this idealized scenario, the energy carried away by the gravitational waves would be equal in all directions. The newly formed large black holes would remain right where the two previously once merged. Now think of it like a cosmic rocket engine. When the rocket fires, it expels hot gases in one direction and the rocket itself moves in the opposite direction. Similarly, when merging black holes system emits a burst of asymmetric gravitational wave in one direction, the newly formed larger black hole receives an equal and opposite kick in the opposite direction. This is a direct consequence of the conservation of the momentum. This is the gravitational recoil, and it's not a gentle nudge. The kick can be incredibly powerful depending on the masses, spins, and orbital configuration of the merging black holes. The recoil velocity can range from a few tenths of kilometer per second all the way up to thousands of kilometers per second. The fastest theoretical kick ever predicted, when the black hole have roughly equal masses and their spins are strongly misaligned. For a long time, these kicks were purely theoretical, while the general relativity equations predicted them. Actually, observing such an event was astronomically difficult. Not only do we need to detect the gravitational waves themselves, but we also need to be able to infer the precise directionality and asymmetric from their subtle signals. It's like trying to tell if a massive bell was rung by an off center strike just by listening to the fading echoes a billion miles away. So, when and how do we finally get direct evidence of this astounding phenomena? While scientists have seen indirect evidence suggesting black hole kicks in the past, for example, quasars with unusually offset supermassive black holes. A direct measurement from gravitational wave was therefore a holy grail. The breakthrough came from analyzing an event designated GW 200-129, detected by the LIGO-Virgo collaboration. This was the merger of two black holes, resulting in a new, more massive black hole. But what made this event special was the precise characteristics of the gravitational wave signal. Scientists meticulously analyzed the waveform, the specific pattern of the gravitational waves, which contained information about the mass, spin, and the orientation of the merging black holes. Through advanced computational modeling, they were able to reconstruct the merger in a very great detail. While not the maximum theoretical kick of 5,000 kilometers per second, this observed kick was still substantial, estimated to be hundreds of kilometers per second. This confirmed that the black hole do indeed get gravitational recoiled. It proved that these cosmic billiard shots are not just possible, but they are happening, and we are now able to we have the tool to measure them in great details. This wasn't just a confirmation of the prediction, it opened up a new avenue of the astrophysical research. We can now begin to sort of quantify these kicks, understanding their prevalence and model their effects on the cosmos. The universe isn't just about things pulling everything together, it's about things being violently pushed apart. How exactly do you measure a kick from a ripple in space-time? It's incredibly complex. Imagine the gravitational wave signals as sophisticated musical chords. The pitch, the volume, the timbre of what the chord tells us about the instrument. How they are interacting with and even with each other, and the force with which they are being played. All of this can be estimated by just hearing that. So, by carefully analyzing the phase and the amplitude of the gravitational wave signal as it swept across the LIGO detector and comparing it to detailed simulation of the black hole mergers with varying parameters, scientists could deduce the asymmetry in the emitted gravitational radiation. This asymmetry directly translates into a recoil velocity for the remnant black hole. It's an outstanding feat of theoretical physics, computational power, and engineering precision. So, a newborn black hole gets a massive kick. What does that mean for the universe? The implications are profound and far reaching. The runaway black hole is the first one. A kick of several hundreds of thousands of kilometers per second is enough to eject the black hole from its host galaxy. A typical galaxy like our Milky Way has escape velocity, and therefore the speed you need to reach to break free from the gravitational pull of around 500 to 600 kilometers per second. So if a black hole gets a kick exceeding that, it becomes a runaway black hole, hurtling through intergalactic space, a solitary wanderer in the cosmic void. Imagine a supermassive black hole, the anchor of its galaxy, suddenly being kicked out. What happens to the galaxy? Does it unravel? Does the star formation ceases? These are active questions. Impact on the galaxy evolution is a second point. Supermassive black holes at the center of the galaxy are thought to play a crucial role in the galaxy evolution, regulating star formation and shaping their galactical environment. If these central black holes are frequently kicked out, it could fundamentally alter how galaxies grows and evolve. And third one is the black hole demographics. The presence and distribution of black holes in the universe could be a different from what we always assumed. There might be a significant population of these runaway black holes traversing the universe far from any galactical home, making them incredibly difficult to detect. This changes our understanding of the cosmic sensors of the black hole. Next is the gravitational wave signatures. The future generation of the gravitational waves detectors, like the proposed LISA mission in space, will be even more sensitive. They could potentially detect and subtle memory of these kicks in the gravitational wave background, or even directly track runaway supermassive black hole through the universe. From the collapsing star that formed them to the spiraling dance of merger to the powerful recoil that can launch them at mind boggling speeds, black holes are proving to be anything but static. They are active, dynamic players in the cosmic drama, capable of shaping galaxies and wandering alone through vastness of intergalactical space. This new direct measurement of the gravitational recoil isn't just a testament to Einstein's enduring genius, but also to the relentless curiosity and ingenuity of the humanity. It shows us that even the most extreme corner of our universe are slowly but surely revealing their secrets. So, next time when you gaze up at the night sky, remember that out there somewhere a newborn black hole might just be getting the most powerful kick of its life, embarking on a solitary supersonic journey across the cosmos. So friends, what do you think about these runaway black holes? Let me know in the comments below. And if you enjoyed this journey into extreme astrophysics, please like this video, subscribe our channel for more cosmic exploration, and hit that notification bell so you don't miss out any next deep dive. Thank you for joining on this incredible adventure. Until next time, keep looking up and keep wondering.